So thank you for attending our talk. This is Friday the 13th, JSON attacks. We have been already introduced, but I'm Alvaro, he's Alex. He's from Ukraine, I'm from Spain, so please bear with our strong accents. We'll try to make our best. So we have a lot of things to cover today, so let's jump straight into it. Last year was the year of the Java deserialization attacks. It was like all over the news. And this is weird because this was a very well-known attack since at least 2011. And probably the reason that it didn't got into the news like before is because the lack of a good remote code execution gadget in like a popular library like the one that Christopher Hoff and Gabriel Lorenz found in the Apache Commons collection library. And that probably made the community to kind of ignore this vulnerability category altogether, at least for Java. So at that time, the solution by security researchers and consultants were like, stop using Java deserialization or serialization altogether. And developers were like, well, yeah, I would love to do so, but I have these objects that I need to store in my database, or I need to send across a wire, and I need to serialize them somehow. So these same consultants and researchers said, like, okay, then use a secure or JSON or XML serializer instead. We already have some history with finding vulnerabilities, remote code execution vulnerabilities in XML serializers like XStream or, for example, XML decoder. So we focus our research on the JSON serializers. So the goal for this talk is twofold. First of all, check if the JSON serializers and libraries are any better than the Java and .NET serializers, and also to raise some awareness around the .NET serialization attacks. Because we saw before that until this remote code execution gadget was found in Java, no one was paying attention. So what we are going to do is release remote code execution gadgets for .NET serializer so that people start like paying attention to .NET and start fixing these kind of vulnerabilities. So the talk is like 3 different sections. We will start like with JSON. We will present libraries that are vulnerable to these attacks, gadgets to attack them. We will show you some demos on web application frameworks. And then we will move completely different section that is .NET serializers. And we will finish with generalizing the attacks to any format, any serializer. So with that, let's jump straight into the JSON section. Just to set the expectation here, we are talking about JSON not like when used by, I don't know, JavaScript to exchange simple data or JavaScript objects, but to replace Java or .NET serializer, which means that we need to serialize Java and .NET objects, which means that we need to handle or support some of the object-oriented programming features, like how I'm going to deal, or how I'm going to serialize a Java lang object, or how I'm going to serialize a system object in .NET, how I'm going to deal with generics, with polymorphism, and so on. So a very quick recap on how the Java attacks worked. Basically, the attacker was able to send an untrusted stream of data, which contained both data and also some type discriminators. That is nothing else than the class name that should be instantiated by the deserializer. So these deserializers, in this case, the object input stream in the Java JRE, was basically instantiating an instance of this type that was controlled by the attacker, and then invoking some callbacks, in this case, the read object and read resolve. So the attackers were able to craft gadget chains that is nothing else than different classes put together in order to get arbitrary code execution, but starting with some of this method of this callback invocation, in this case, the read object and read resolve. However, for JSON, or the libraries, the JSON parsers, do not normally invoke these read object and read resolve methods because they have nothing to do with Java deserialization. So we need a different way to start a gadget chain leading to this arbitrary code execution. So in order to do that, we analyze how these libraries and parsers reconstruct the objects when they receive the JSON data. And basically, they call a default constructor. That is the one with no parameters, so it's not very interesting from an attacker point of view. And then they either use the reflection or setters in order to populate all the fields and properties for the object that they are reconstructing. Some of them also invoke some special deserialization constructor or some callbacks like the read object, read resolve. Some of them also invoke the .NET specific type converters. That is something that we don't have time to cover in this talk, but it's in our paper that was published for the Black Hat version of this talk. And in addition, there are also some common methods that are normally invoked, like, for example, hash code or equals may get invoked during the deserialization of a hash map. To a string may get invoked during when raising an exception, for example. Finalize is always invoked by the garbage collector when claiming the memory for that object. So there are different methods that are going to be invoked during the deserialization or reconstruction of these objects. But by far, the ones that are most used are the setters, or most common are the setters. So we spend some time looking for gadget chains starting with a setter and leading to arbitrary code execution to use to attack these libraries. So now Alex will show you some of the gadgets that we found.
Let's have a look on a few setter gadgets in .NET. All of them can lead to code execution. Some of them have own requirements and limitations, but we believe that it's not very difficult to pick up proper one for specific library or specific case. The first our gadget is a setter of path property in assembler installer type. It allows execution of code execution during library loading from path controlled by an attacker. There is no additional requirements if assembly with payload is on local machine. But in case of remote resources, network resources, newer .NET frameworks may have some additional security checks. The next two gadgets use XAML parser. We will show a bit later how it can be used for arbitrary method invocation. So, setter of property inspector font and color data from workflow designer type requires single threaded apartment thread. It's quite strong requirement, but if your target has this configuration, you will be able to get remote code execution. The next gadget, setter of source property in resource dictionary type, has a few requirements to JSON unmarshaller. It should call setter for types that implement iDictionary interface. Often in such cases, JSON unmarshallers are just populating key value pairs. Also, it should be able to reconstruct system URI objects, and this type doesn't have default constructor. But usually, parser can do this because they need to work with this type. And finally, our last gadget is from object data provider type. It's quite flexible and allows a few attack vectors. As a result, we were able to use it in almost all our unmarshallers and formatters. Let's look on a call diagram of this gadget. Setter will call refresh method that will invoke begin query. Begin query will call query worker, and finally, in invoke method on instance, we can see the line that will call our arbitrary method. On this slide, we can see an example of payload that will pop up calculator for unsafe configuration of JSON.NET parser. The main attack vectors for this gadget are the next. We can call non-default constructor with own parameters. Also, we can invoke public methods on unmarshalled objects. Or we can call any public method, including static ones with own parameters. Java has own setter gadget as well. After our last year research in GNDI injection attacks, we have found a few setters with GNDI lookup calls. By the way, recently Oracle disabled RMI and Corba vectors, but LDAP vector still works, so problem is not solved. The first our gadget is set session factory GNDI name from statistics service class. We already mentioned it on our Black Hat talk at 2016. The very similar to it is the next gadget, toString from a remote client user transaction class. And finally, set autocommit gadget from already known class, GDBC route set impl. This class is from GRE libraries, so doesn't require additional dependencies. As we can see in this setter, we will call connect function. And here we can notice initial context lookup call with our value from data source name properties. So we will be able to get remote code execution. Apart from mentioned gadgets that allows code execution by themselves, we have a couple other interesting gadgets. Some of them can be used as building blocks for gadget chains. For example, binding sort set data member in .NET or string template to string in Java can be used for arbitrary getter calls. So we can use other gadgets in getters to get code execution. Other gadgets can be used for non-RCE attacks. For example, set inner XML in XML data document or set data view setting collection string from data view manager type can be used for XML external entities attack in some version on .NET framework. Now Alvaro will show where we can use all these gadgets.
So we analyzed like a bunch of different JSON libraries for both Java and .NET. And we figured out these 3 high-level requirements for a library to be vulnerable. So first of all, the library needs, or the attacker needs to be able to control the type that is going to be instantiated by the library. So that means that in the JSON data, you will normally see like some attributes, like for example, with this underscore type, dollar type, class name, Java class name, some attributes which contain a value that looks like a Java namespace or a .NET assembly. And then those values, those strings are going to be used by the library to instantiate those types in the server. Then the library is going to invoke some methods on those reconstructed objects. We already saw that, for example, finalize will always get invoked, and that most libraries will invoke setters. And last but not least, the attacker needs to be able to have like a large enough gadget space for those methods to be able to craft these gadget chains leading to arbitrary code execution. So we categorize all the libraries that we analyzed, and we use 2 different factors for this categorization. The first one is whether these libraries are including the type discriminator, that is the type name by default in the data, or the developers need to enable some configuration setting for the library to include and process this type information. And the second factor is how do they protect against some kind of type attacks. So how do they control the types? So some of the libraries perform just a cast operation after the deserialization has completed, which means that by that time, the payload has already been executed, and when you get the cast exception, it's already too late. And some of them performs what we call the inspection of the expected type object graph, which sounds like a little bit complex, but it's nothing else than taking the object graph of what I'm expecting. Like, for example, I'm expecting a user instance or a card instance. Then I'm going to inspect the object graph. And for each of the fields or properties, when deserializing the data from the JSON data, I'm basically going to check the assignability for what I get to what I'm expecting. So if I'm expecting, for example, I'm deserializing the property, the name property for the user, I'm expecting a system string, and I'm not supposed to get an object data provider, that is the gadget that I showed you before. So because object data provider is not assignable to string, I will raise an exception and will not process to deserialize that object data provider. There are other libraries that, in addition to that, they create like a wide list of allowed types at construction time, which means that they inspect the object graph, then they take all the types that they can find in the object graph, and then they build a wide list with those types. So at runtime time, when deserializing untrusted data, they apply that wide list and say, okay, I'm expecting these 5 types, and you're sending me some type that is not in my wide list, so I'm not going to continue with this. We found that this is still vulnerable if attackers can either control the expected type, that you may think that is not common, but we will show you some real-world examples in very popular CMS. And also, if the attacker can find an injection point in the object graph that is assignable to their payload. So let's say, for example, that we have this object graph here.
Oops.
Sorry.
It's already okay. Alvaro, okay.
I don't know where is the pointer. Okay, here we are. And okay. So imagine that we have this object graph here, and any properties in red are those that are assignable to, for example, any other type. Like, for example, in .NET, the hash table or array list are generic collections, so they contain items that can be assignable to any type. Or if you have like a dictionary of string objects, you can place your payload there. Or maybe you have, like, for example, an exception field or property, but attackers can use any exception. So they can, for example, use the validation exception, which contains a value property that is a system object, so they can inject the payload there. So with that, this is the summary of the libraries that we analyzed. The ones in red are the ones that are vulnerable by default, so they should not be used with untrusted data. Basically, they include the type information by default, and then they perform just a cast operation, so they perform no type control at all. Then they invoke setters. You can use the setter gadgets that we presented in order to get arbitrary code execution. Then we have the yellow and orange ones, which are not insecure by default, but depending on how developers use them, they may make them vulnerable. So normally they don't include the type information by default, and they perform some of these inspection of expected type object graph. And you may think that finding an application that is using these libraries and meeting or satisfying both requirements is difficult, but it's kind of the other way around, because if the developers, for example, contains a system object property in their object graph, they will be forced to include the type information in the JSON data, otherwise they won't be able to serialize it. And if you find an application that is including this type information, it's probably because they have some system object or some generic collection properties in their object graph. Then we have the one in green, that is JSON. We put it in green not because it's completely secure. You can still implement a type adapter that is vulnerable, but I mean, you have to do it like in purpose. And in addition, they don't invoke any methods. They don't invoke setters. So the only entry point for you is finalize, which is kind of limited in the gadget space. So these are some of the libraries that we saw. For example, fastJSON was one of the ones in red. As I said, should never be used with untrusted data. We found, for example, a CMS called Calico CMS that was taking untrusted data and using fastJSON to deserialize it. You should never do that. JavaScript serializer is one of the .NET native JSON serializers. By default, it does not include the type information, so it's secure. However, developers can initiate it by passing a type resolver, which means that the library will include and process the type information. And because it does just post-deserialization cast operation as the type control, it will be vulnerable, and it cannot be used with untrusted data when used with type resolvers. Then we have the data contract JSON serializer, that is another of the .NET native JSON libraries. And this is probably one of the most secure because it's limited. It cannot serialize any type. It's quite limited. But it's applying this technique of creating a whitelist based on the object graph types, and then applying that whitelist at runtime time. But we found, like we said before, that it's still vulnerable if attacker can control the expected type. So here's an example from GitHub where you can see that the expected type is controlled because it's actually coming from a cookie. And you will see that in an example that we showed you before in a demo. So last but not least, JSON.NET is probably the most popular JSON library for .NET. It's even recommended by Microsoft over their own JavaScript serializer, or the data contract JSON serializer. By default, it's secure because it does not include the type information. But again, developers can enable this type name handling setting in order to include this type information. And if that is the case and the attacker can find an entry point, it will be vulnerable. So this is another example from GitHub. We have this message class here. It contains just one property, but this property happens to be a system object property, which means that in order to be serialized, as we said before, the developers need to include the type information along with the data in the JSON data, because otherwise it's not going to be possible to deserialize it. And that's why they use this JSON property annotation here, which is configured to include the type information. So let's show you some examples. So for example, we have this demo for Breeze, that is a .NET framework to build RESTful APIs for data management, entity management. So basically, you expose a REST endpoints to perform operations on your entities, like, for example, add a new record, update a record, delete a record, and so on. And they offer both clients for both .NET and JavaScript. So they use this type name, this global JSON serializer, which is configured, as you can see, line 56, to include the type information when serializing and deserializing system object properties. Then at a different point, it's deserializing untrusted data. And as you can see, line 63, the expected type in this case is safe options. So now we have to do this inspection of the object graph expected type, which is nothing else that taking a look into the safe options type, inspect the object graph, it's just two properties, and see that the second one is a system object, so it's going to be assignable to any type, so we are going to be able to inject our payload here. So let's see if I can play this without breaking PowerPoint. Okay, so this is an application that comes with Breeze. It's one of the sample applications for developers to learn the framework. And as you can see here, if you change the model name of one of the cars, well, it's just sending a request to the endpoint to update one of the records. Now, if we capture the request, you can see what we're expecting. So, for example, the changed name. But we also see an empty safe options dictionary. Now, if we send this request and we analyze the response, we will see that there is this $type attribute that contains something that looks like a .NET class name. So that's because it's using JSON.NET and it's including the type information. So now we are going to use our object data provider gadget in order to invoke the process.start method and pop up a calculator when deserializing the data. So now we're going to replace the empty safe options dictionary with our payload, and we are basically send that to the server that is not running any calculators right now, and as soon as we send it, we will be able to execute any process in the server. So we will get remote code execution. Thank you. So this is a web application framework, meaning that any application built using Breeze was vulnerable to this attack. So a big shout out to Moritz Bechler, who published a similar research to ours, who shares kind of the same premises and conclusion, but he focused exclusively on Java. And he overlapped with our research on both the Jackson and JSON IO libraries, although for the JSON IO, he found a completely different approach. So congrats there. And also he overlaps in our JDBC roasted implementation gadget, which was kind of an obvious choice because it was used previously on the Java deserialization world. But he also found a very interesting gadget, so we highly recommend you to go and visit the MarsalSec white paper that contains a lot of interesting stuff around this kind of attacks. So now we will switch gears and move into the .NET part.
In .NET world, the potential security problems with binary formatter and net data contract serializer were known for the years. The great work of James Forshaw about weaknesses and attack vectors for main .NET formatters was presented at Black Hat 2012, so more than 5 years ago. Anyway, we could not find publicly available good remote code execution gadget chain. There was one published by Florian Gaultier, but it used memory corruption, so it's not very suitable for stable exploit. But we were sure that there should be a lot of way for code execution during .NET deserialization. So we have spent some our time for searching such gadget and have found one that can be used in binary and some other .NET formatters. But after our work was ready and accepted by Black Hat, the same James Forshaw published a couple new RCE gadgets as part of his own research. By the way, not connected with our topic. Anyway, you can find details about this gadget on his post in Google Project Zero blog. Here we will focus on our own. So we will use PS object type. It is part of PowerShell libraries, so it's available on almost all Windows machines. And before we go further, there are a couple of remarks about this gadget. In PowerShell version 1, this type is not serializable, so it's not suitable for attack. But all modern versions of Windows, starting from Windows 8 and Windows Server 2012, are shipped with newer and vulnerable version. The next remark, we reported this issue to Microsoft, and they released a fix. So if you're not ignoring their updates, you should be safe. So PS object uses custom deserializer, and in case of TIM instance, it will call rehydrate TIM instance method. And we can see here that attacker is able to specify own type as element type of array, and deserializer will try to reconstruct object of this type. To find a proper way to do this, deserializer will use figure conversion method. It's quite interesting method for attacker, as there are a lot of ways for attacks. We highlighted only the most obvious one. So we can call non-default constructor with one argument, and we can control its value. Also, we can invoke setters on public properties, so we can use here our mentioned gadgets. And finally, we can call a static public parse method on arbitrary type. Let's try to use, in this case, this one. So, as we said earlier, XAML reader parse can be used for arbitrary method invocation. Here we can see payload that will call process start method with our string as an argument. We can notice here our namespace, assembly, type, method name, and finally calc as an argument. So we can use this payload for start any process. Apart from mentioned binary and net data contract serializer, .NET offers a lot of other formats that can be abused. Unfortunately, we don't have enough time for detailed review of each of them. So we will try to briefly cover them in our talk, and if you're interested in deeper analysis, we can offer out white paper as a good source. So we can group all these .NET formats in two big groups. Formats that are vulnerable in default configuration, like binary formatter, SOAP formatter, and net data contract serializer. Also, we can add here other formatters that internally use them, like loss formatter, object state formatter, binary message formatter. They should not be used with untrusted data, or you have to proper configure them to limit available types. For example, use type binder with whitelisted types. The second group is formatters that are safe in default configuration, like XML serializer, data contract serializer, data contract JSON serializer. But if you are using the weak data contract resolver, by the way, we have met such examples even on official Microsoft documentation, or an attacker is able to control expected type, you will have very serious security problem. And we will show a bit later that in this case, code execution is real even for the most limited formatters, for example, like XML serializer. Now we switch back to Alvaro. He will show our next demo.
Yeah, so because a demo is worth 1,000 slides, let's see if I can play this. So this is Nancy. It's a web application framework for .NET. It's basically very similar to the Sinatra framework for Ruby. Probably that's why it's called Nancy. And, well, they care about security, so they have protections against CSRF, which is good. But the way they implemented it is instead of putting like a unique token into the CSRF cookie directly, they put that in as the property of a special class, and then they serialize this class base64 encoded and put that into the cookie. So the result is that they have this big base64 encoded blob, starting with this AAE8AD, that by the way is the magic number, which means that you got remote code execution. And now, because it's using binary formatter, we can use our PS object gadget to get arbitrary code execution when this cookie is deserialized. So let's see that in action. This is one application built using the Nancy framework. If we check the cookies, we will see that it contains this base64 encoded NC-SARF cookie, which starts with our magic number, which is good. And then if we check the source code, we will see that it's double submitting the same value as part of a hidden form field. So that's good. Double submission is better than single submission. Now, if we replace the value of the cookie with the PS object gadget that is basically configured to run the calculator, we will just paste it as the value of the NC-SARF cookie. We will fill the form, and we will send it to the server. So the framework, when deserializing the NC-SARF cookie, will basically deserialize our untrusted payload and will run the calculator. So we get an exception here, but we have our calculator, so we were able to attack any application built using this Nancy framework. So the last section is generalizing the attack. We saw that this attack is not really specific to JSON. We don't see any JSON-specific stuff being used. So there is nothing really specific to either JSON or the binary formatter for .NET or for the XML serializer. The problem here is that the deserializer needs to reconstruct the objects. And for that, if the attacker can control the type, then they are going to be able to initiate some call graph that they can control and may lead to arbitrary code execution. So again, these are the three simple requirements that we showed you before. Attacker needs to be able to control the type, which means that the type discriminators need to be included in the serialized format. Some methods need to be invoked on the reconstructed object, which is normally always the case because the finalized method will normally be invoked. And also, there should be a gadget or a large enough gadget space for the attackers to craft a gadget chain leading to arbitrary code execution and starting with these invoke methods. The truth is that most of the libraries, most of the serializers will invoke the setter. So the gadgets that we presented here today, the object data provider for .NET and the JDBC raw setting pool for Java are going to be valid gadgets for attacking most of other libraries. So some examples, we found like many of them, but we don't have time or nor the space to present all of them. For example, FSPickler or Subserializer are some .NET libraries that not only work with .NET framework, but also with Silverlight, Windows Mobile, and other frameworks. And they both include the type information by default. One of them performs no type control, it's just doing a post-deserialization cast. And the other one, FSPickler, is doing this object graph inspection, which means that you need to still find an entry point. But both of them should not be used with untrusted data. Then we have Wire, that is now known as Hyperion. This is the serializer for Akka.NET. That is basically the .NET version of the famous Scala and Java library to do some actor-based concurrency. And basically, we have these actors that are exchanging messages that used to be serialized with JSON.NET using the unsafe configuration, by the way, the type name handling equals all, so including the type information. And now they replace that with this Hyperion serializer that is a custom serializer, which is basically including type information, invoking setters, and also invoking some other callbacks, so it's vulnerable. Also, be aware of rolling your own format. When we notify Nancy about their vulnerability, they said that they were using a different format in their pre-release 2.x branch. And we took a look at the new format, which was basically custom JSON format that they implemented on their own instead of using, I don't know, JSON.NET or some existing libraries. So we took a look at this custom format, and we saw that they were using the type discriminator. They were including the type discriminator and then invoking the setter, so it was also vulnerable to remote code execution. Then we have .NET Nuke, CMS, that is one of the most, or if not the most popular CMS for .NET, which is kind of wrapping XML serializer. So instead of just using XML serializer with a fixed type, is basically sending the expected type and then the payload for the XML serializer. This was kind of a challenge for us because XML serializer, as Alex said before, is the most limited serializer in the .NET family. So if we could get arbitrary code execution here, we were kind of confident that we were going to be able to get arbitrary code execution for any of the other serializers. So we tried to use our object data provider gadget that was XML serializer friendly, so far so good. But then we could not use the process to invoke the process.start because process is a type which contains interface members. That is one of the limitations for this serializer. That was not a big problem because we can use other payloads, like, for example, invoke the XAML reader load method or the object state formatter deserialize method, or you can even look in the target application class path for custom gadgets to use. So, for example, .NET Nuke contains this file system utils class, which is kind of handy for hackers because it contains some methods that can be used to deploy web shells or to read arbitrary files into the HTTP response and send the contents back to the attacker. So that problem was solved, and then we have another problem. Basically, XML serializer used this whitelist approach, so it's building this whitelist at construction time that then is applying at runtime time. And if we analyze the object graph of the object data provider type, we will find one system object property, which it will be included in the whitelist. But at runtime, we will be sending something else. We will be sending the file system utils or the XAML reader or something else. So it won't be in the whitelist, and then it will make the deserialization to fail. So we found this clever trick of using a parameterized type and putting our runtime types as the parameterized types for the payload. And then that makes XML serializer to learn about our runtime types at construction time. I don't know if that makes any sense. Anyway, with that, we were able to get arbitrary code execution remotely on any instance of .NET Nuke. And basically, that was kind of simple. So we have this DNN personalization cookie that is read at some point. For example, when visiting the 404 error page, this piece of code is executed. And then this is reading the cookie that contains an XML value, and then it's passing that XML to the deserialized has table XML method. Then in this method, we are basically extracting the type of the expected type from the XML and using that to instantiate a XML serializer instance in line 201, which basically means that we now control the expected type. So that's what we were talking before. That is something that is kind of common. And then the rest of the cookie, the rest of the XML is deserialized using this XML deserializer. So this is how a regular cookie looks like. Basically, I'm saying, OK, I'm sending a system Boolean, and this is the system Boolean that I'm sending serialized with XML serializer. This is our payload, which basically say, I'm sending this, and by the way, include these types into the whitelist, the file system utils one, for example. And this, the inner box, is the payload that is going to be deserialized by XML serializer. As you can see here, we are using the file system utils class in .NET Nuke class path to use the pull file method to download our web shell and deploy it on the target server. So with that, let's see if this plays. So this is a .NET Nuke out-of-the-box installation. If we visit a non-existent page, we will get the 404 error page, which we know that is going to read this DNN personalization cookie. So now if we intercept the request with any proxy and include this DNN personalization cookie, like for example, let's use verb, and then the cookie is not present here, but we know because we have saw the source code that is going to be processed. So let's put it here, and we will basically copy-paste the piece of XML that I showed you before. That is basically using the file system utils type, the pull file method, to download and deploy the web shell. So let's copy-paste this here. Let's format it a little bit. And now, if we check in the server side, the one that is running the CMS, we will see that there is no cell ASPX file. And now, as soon as we send the request and this gets deserialized, we will get our cell ASPX deployed into the server and ready for use by the attacker. So now we only have to go and visit this cell ASPX, get our web shell, and then we can interact with the server and run any commands. Thank you. So with that, we're running out of time. So to quickly wrap up, do not use any, do not deserialize untrusted data. We saw that this is not a problem in Java deserialization. It's not a problem in binary formatted in .NET or JSON.NET. It's basically a problem in deserializing untrusted data with type controlled by the attacker. So try to not do that, and if you have to, try to evaluate the security of the library that you are using. Avoid libraries that are performing just cast operations and not a strict type inspection of the expected type. Including the type discriminator, the type names, is necessary but not sufficient. But if you find a serializer format that includes the type discriminators, that's a good indicator that it's going to be vulnerable. And also, don't use information or data controlled by the attacker as the expected type, because that means basically that they can control the object graph, and so it's game over. And last but not least, do not roll your own format if you're not aware of this kind of attacks and don't know how these things can break. So with that, thank you very much. These are our email address if you have any questions, and if you have any questions, we can take it here.